time and space. It sounds always philosophical. And part of it is, but it's really necessary that we have a clear understanding what we are talking about in this course. If you have physics background, then some of that comes automatically, but not all of us have a strong science physics background. So we need to do some of that in more detail. Two questions have to be answered first. What is time and what is embodiment? Those two things are essential. Then we can start interfacing with time, specifying and ultimately satisfying timing requirements. This is what this chapter is basically about. So, item number 1, what is time? Time is when the lecturer is sitting in front of the students and nothing happens. Then, how would you define time in a real-time physical environment? Maybe not logical, huh? Because change of the bits. Okay, is that how you define time?
No, it's time can pass without it's changing.
Speak up.
Time can pass without it's changing. So,
time passes without anything changing?
it's possible, right? But in that sense, time is
Okay. So if you close your eyes, don't imagine you close your eyes. And you hold your ears closed. Time still passes? Probably. Okay. Okay. Who is certain time still passes? You're certain time still passes? You're certain? You're not quite certain. So what makes you certain that time still passes when you shut off your senses? It's a belief. You're the time believers. You believe in time without evidence. No, it's important. Do you believe in time without evidence? You have evidence?
Yeah.
If you close your eyes and you shut your ears, what's the evidence?
I'm thinking about things that's different from what I was thinking about when I closed my eyes.
You're thinking about things.
Yeah. And I'm assuming that I'm in a world that...
How fast are you thinking?
I don't know, but I'm not stationary.
That's an interesting aspect. So you observe yourself, you observe your own brain ticking.
That I'm in a world or whatever that needs time to keep moving.
Yeah.
Keep thinking.
How do you know this is not an illusion?
Oh, I don't. But then you get to the whole, like, we could just be created a second ago and all have the memories that we do now.
Uh-huh.
All that stuff.
Okay. Okay. Interesting. We have basically talked ourselves into these two kind of principal ideas about time. You can think of time in a Platonism way or a reductionist way. The old Greeks were with you. They thought time is an intrinsic part of nature, and this happens whether I'm looking or not. Doesn't depend on me. If I close my eyes and I'm not observing anything, time still is there. This is a Newton kind of angle on the world. And the other one is a more reductionist, a more scientific approach. If you don't observe something, you actually know whether it's there. If nothing changes, if you do not observe any kind of change in your environment, you cannot know whether there is time passing or not. without any change in your environment. And you have an interesting observation point because you can observe your own brain. Maybe? Not quite clear. But as long as you can observe something in your environment which changes, this is your evidence of time. Which brings us to the next question. If you look at events happening, what happens to time in between these events? Is that kind of interpolated? Do we care what happens to time in between? Is it we have time events, time events, time events? The time in between is, do we care? The time in between is linear?
Like, at least when you're in the CPU, you only care about what happens when the clock hits. And like, well, there's nothing happens in between those cycles.
Yeah.
But it's changed when the clock happens.
Yeah. And this is actually exactly the reductionist approach to the whole thing. It is utterly irrelevant what you assume, what happens between these events. You cannot prove it either way anyway, because that's the whole point of looking at it in the reductionist way. I can only prove things which I can observe, verify things which I can observe by some form of measurement. Nothing happens, I'm rather not making any assumptions. Maybe my time passes logarithmically between these events. Can you disprove me? Say again?
With respect to what?
Exactly. That it starts also with respect to what, because you don't measure any time anyway. But the point is, do you assume that there is any time in between observable events? If you answer yes, there is any time passing, then the next question is, how does it pass? And we are actually back to the beginning, and we have to assume something about the time passing in between. Right?
In the real world, there's not a kind of an atomic event, but in the computer, the program like
In the real world, there is not such thing as an atomic event. Don't talk to physicists about that in those words. They would probably tell you something else. The philosophical angle on that one, is there a granularity to everything? And the current state of the world for the last 120 years or so says yes. The world is not a continuum of any sort. We have discrete events to observe from that one. Everything else is your imagination. Unless you give me any evidence for it. Good. What does math give us? Can I define time in a mathy kind of way? Can I have a time algebra? Say again? Logical time. Okay. Let's do math. Does that make sense? If I have a number of timing events, x is earlier than y is earlier than z, then x is earlier than z. X is earlier than z. You agree? Linearity. If one is earlier than the other one, and the middle one is earlier than the other one as well, then they are not the same. Okay. Irreflexibility. So the event cannot be earlier than itself. Okay, maybe. Density, which means for every two events, I have another event which is in the middle between these events. Now you're going. Yes. Continuity. If I know that two events in the past were ordered, if I add something to that, are they still ordered for all future times? That's a good question. What does plus mean? How did I measure x and y in the first place? On which system did I measure x and y? Did I measure x and y on the same system? Did I measure x and y on 2 different laptops side by side? How far can you get with these kind of math environments? The real world is different in the sense that all of your clocks have a granularity to it. So whether you believe in reductionism or not, your computer clock has a granularity. That's not disputable, right? Because all of your technical interfaces to any kind of clock mechanism is based on something oscillating. So you have clearly a maximum resolution of your time, always. But that's not the worst thing. When it becomes much more interesting is your clocks are asynchronous because they're all looking at different events. And the fact that you're sitting at different ends of the room already makes it almost impossible to synchronize in a complete and perfect world to the same clock. Why? Signal delays. Huh? So whatever you receive from your environment, even here in this room, is from the past. And the further your communication partner is away, the deeper in the past this information is. If you now try to synchronize your clocks, with whom do you want to synchronize? Somebody who's closer by? How do you synchronize the clock of all of us in this room in a precise way? How do you model all the signal delays, which has to automatically happen because of physical distance? Or we all have to sit on the same chair, and then we can synchronize our clocks. No, let's not try that. Okay. This is math, and besides rather trivial assumptions, you're not getting very much out of that perspective at the moment, because the fact that clocks are asynchronous and not synchronized in that sense has to be modeled here as well. This makes this algebra significantly more complex than what you see at these trivial equations here on the screen. So from a physical perspective, 1676, we already were aware that there is a speed of light, which is interesting, even though we didn't conclude all the interesting stuff of it back then. But I'm always amazed how long ago that actually is that we discovered that there's something like a speed of light. And in complete ignorance of that, Newton's Principia Mathematica still assumed an absolute time. Even though that was already, if you look at it from today's perspective, that could have already been concluded as this is no longer true. There is no such thing as an absolute time. Okay. And this has only been ultimately destroyed by the concept of Poincaré and Einstein in the beginning of the 20th century. And a few years later, we also destroyed the independence of time and space in the same kind of logical reasoning which followed from that. Okay. This is all abstract. Who cares? You do. No, you do, because otherwise you're never sending anything into space. Because the clocks in satellites, actually simply directly have to implement that. You are in higher altitudes, you're in higher orbits, your clocks, you can measure this directly, will behave exactly how this has been predicted, and you have to compensate for that. You have to be aware of that. So how do we classically measure time? How have we been measuring time in ancient times? What's our, as humans, what access do we have, what possibilities do we have of measuring time? Looking at the sun, yes, that's the first one. It basically gives you some rough estimation in terms of sundials. You look at the shadow on the ground somewhere, and it's not an overly precise form of measurement, but it's an amazingly good measurement in terms of absolute precision, because this is your reference has not drifting away. You're always directly referring to what our time is actually defined by, namely the sun. That's interesting. Okay, so we are beyond sundials for a few thousand years. What was the next evolutionary step beyond sundials? What is the next thing we discovered? Say again? Pendulums. That's a common misconception, and it's amazingly late in human development, in human technology development, that pendulums have been discovered and used for time measurement. We always perceive pendulums as this is a real old-fashioned way because they look so old-fashioned. But in terms of the actual technology development, they came after quite a number of other forms of measuring time. For example, most people would assume that measuring times by little weights which are moved around by springs, what you have in wristwatches, not this one, but for mechanical wristwatches, where you have little springs which are actually moving around. This is older than pendulum watches. Which most people go, no, pendulum is the old stuff. And then we got these small wristwatches, but using springs for measuring time is actually older than that, which is funny. Yeah? Yeah, moving sand. Yeah. So everything which has a slow progression and has a controllable progression. So a movement of sand in an hourglass is quite reproducible. And actually historically, which we are not quite aware of today anymore, sand was not the dominant way of doing that, but water has been used instead. Because water you can actually easily measure longer time spans, because having a lorry full of sand to measure the time of day progressing is kind of cumbersome, but having a tank or a puddle or a pond of some sort where water moves from one side to the other is mechanically much easier to build and to design. So the earlier clocks were actually based on movement of water rather than movement of sand. Sand is great for small measurements, but not for a whole day. Yeah, so all that kind of stuff has been done. And in 1675, we have Greenwich Mean Time, which is still a term which you're aware of today. This is that old. That's been introduced. And you can imagine in 1675 they didn't exactly have very precise clocks to do that. So this was more of a agreement. We need to define time, agree on time, to drive our technology development in this country or the whole world in a sensible way. So the inside of it doesn't cut it anymore. If everybody says my time is this and this time is that, and every village has its own little clock tower and it goes bang bang at a different time of the day, it's not cutting it anymore. We need to have, for some kind of an industrial development, we need to have a common time. And so we have the Greenwich Mean Time introduced there, which has been amended many times in terms of universal time, a number of incarnations for that one. 1927, we have introduced crystal clocks for the first time, and the universal time, which has been produced in Greenwich, is slowly integrating more phenomena which we understand, mostly about our own planet, how the planet is slowing down, how the planet is moving in specific ways. And this is more and more integrated into those more and more complex equations to do that. 1955, we added atomic clocks to the whole thing. And there's a bit of a split up in the community here. So we're in the open source community of time. We have done a bit of a branching into a renegade community, which said that no, actually the time is defined by the movement of the solar system, not what you do in your atomic watches. So there is the ephemeris time, which is much closer based on the movement of the planets than the adjustment of atomic clocks. Since '64, we have the UTC time, Universal Time Coordinated, and that's basically a blend and a mixture of all the different possibilities which we have, which regularly corrects our time understanding on this planet by half a second forwards and backwards on a very fine granularity. And we are making sure at the moment, we are guaranteeing that the absolute difference between the Universal Time Coordinated and the International Atomic Time is always kept below half a second. It's not overly precise if you think about things, but this is the framework in which we pledge to stay since the 60s. And this is how you can define a second, depending what possibilities you have. The first definition of a second is, of course, in a way, the original definition of a second, based on the weird concept that days need to have 24 hours. What happened to the decimal system? Who came up with the idea of splitting up things in 60 minutes instead of 100 minutes? We? Who is we? Do you also know which part of humanity came up with that idea? Close, Babylonian, but yeah. Same direction. So it's a lot of historical developments which goes into that one, because we thought having base 6 or base 12 was a better idea, and we still count times with base 12, right? Or depending how you look at it. So this is a definition of a second with respect to a solar day. It leaves you with one problem left. What's a solar day? Ephemeris time says that I'm not looking at a single solar day, because the solar day changes over the year. So I'm looking at the overall development of a year. It's a bit more precise. Or you say, go away, I don't care about your suns and planets. I just say that after 9,192,635,31,770 periods of my isotope, which I can observe here, I call it a second. Okay. So you see, it's a non-trivial operation to agree on time. How do you agree on time on your laptop? How precise can you get your time? Is any of that relevant for us? Can be very relevant, so depending on it. In the world of real-time systems, we usually define real-time as some reference which can be external, or you can generate it yourself. And then we are calling this our reference time, and we don't care about the semantic beyond that point anymore. We just have to define it clearly in the beginning. What is our reference to real time? Does it refer to international coordinated time of some sort? Does it refer to some 32-bit, 64-bit timer in your CPU? Is that your real time? Just have to be clear about what that means. But I think we have fairly well understood that so far. Generating your own time frame or using an existing one. Why don't we all use the same time frame internationally everywhere for all real-time systems? Physical distance. You just can't. Because if you have systems on different continents, there is significant time passing between these things. Hard synchronizing them is just physically not possible. Can you physically hard synchronize your devices in the same room? I can connect them together. Is this being done? Do you know where this is being done? Or how would you connect them together? What would you do to connect them together for the purpose of having a synchronized time?
They both have two crystals oscillating at the same frequency.
Mm-hmm.
If you just say this one's the real time and then transfer it to the other one.
Okay. How do you synchronize your devices here in this room? Do you have a clock in your laptop, right? Will this clock on your laptop show the same time on all of your screens?
Down to a second, maybe, yeah.
Down to a second, maybe? It's not particularly precise. You know how your laptop knows what time it is? Yes, network time protocol. You just usually synchronize something like once a day with some time server someplace. Where is this time server located? Anybody knows? Well, can you come up with your own time server in your house at home? Sure, it's an open protocol. You can just make your own time and synchronize your laptop via NTP with your house. Because my house defines time. Maybe your laptop is not doing this at the moment, so there are a number of time servers in Australia and Asia around. And by default, your laptops will use one of those. Not overly precise, right? What kind of connection do you have to these time servers? The internet. The Australian internet. That sounds bad. But the internet, which means your latencies, which you have in there, are already quite significant. How do you adjust the time via the internet? Internet is not exactly a predictable communication system. So you send some message to your time server, someplace in Asia, and this server sends you some information back. Yep, it's 3 o'clock in the afternoon. And your laptop goes, okay. It's a bit more involved than that. Because you, for example, have to start by estimating what is actually the time delay which passes in here. So you do this a number of times. You send a number of messages back and forth. You take some statistical averages, what the response times were. You make some assumptions that the other server is probably in the middle of these delays. Right? You don't really know that. If the message towards the server is always double as fast as the message in the opposite direction, how can you ever know that? You only send something out and you get something back eventually. You don't know in which time relation this happens. So this is all heuristics and assumptions which you do there, and it works well for about a second. Yeah?
So, about how long would the communication take between the laptop and time server?
Well, exactly what your ping says when you measure the delay to any other device as well. So we're talking microseconds,
So
many hundred microseconds.
if it's just like a time on a laptop that we look at to see roughly what time it is, do we care about that half a second?
No, because you don't care about seconds. You have roughly the precision of seconds on your laptops, and that's as good as it has to be for that kind of purpose. If you control a nuclear reactor, you probably will not synchronize your clocks that way. Probably want to do this a bit better.
Why is it important that, well, for a nuclear reactor, you want to have it internally
Yes.
clock nicely, but do you have to have your effective the same second as the effective down the road? Or why does that matter? Because isn't...
Okay, let me put this into context. Your nuclear reactor is producing electricity usually, and it has to feed this into the electricity grid somewhere else. Now, you have other nuclear reactors. You have other coal power plants somewhere else down the same wire, down the same road. And it is kind of very important that they stay in synchronization. Because if you don't agree on the same time, then your whole power grid goes down.
But we can communicate faster than 50 hertz or whatever the power phases are at, can't we?
Yes, but you have to communicate a lot faster than those 50 hertz because if you only communicate on a position of, say, 50 hertz and you're just off by one wavelength, you kill your whole power grid. You're dead.
But isn't being off by one whole wavelength being off by whatever that fraction of a second is, which is way more than our speeds? So,
yeah.
Okay.
Which means you're opening up now another discussion, namely, why would I communicate the actual time to another entity which I want to work with? Why don't I make this dependent on the actual information which I'm transferring, namely in that case, the actual energy which I pump down the line? Maybe the other power plant would be wise to just use that energy which comes in as my time base, rather than trying to synchronize clocks. Why don't I synchronize clocks wirelessly? Wouldn't that be a more clever way of doing that? Just sending out clock information by some wireless tower someplace, and I'm just synchronizing my clocks to just that. Of course. The whole world is doing that, but Australia. So this thing here synchronizes in the US, in Europe, in China, in Japan, Korea, and it did so all over this place, which constantly reminds me that I have to go traveling on a regular basis because otherwise my clock drifts away. But Australia doesn't have any wireless time signal, which is a pity, and that would make it a lot easier. If you, for example, buy a simple bedside table in Europe anywhere, they're all wirelessly controlled. You don't have to set any of them. You just put them in your bedside and the time is there, because as long as you get this wireless signal, it's all there. Which is one of the reasons why people are more on time. I don't know. Hard to say. But it's very easy. Another classical way of synchronizing clocks is something you're probably also not that aware of. Has been used in Europe for decades, very long time. Namely synchronizing your clock based on the power grid. The power grid at 50 or 60 hertz, depending on what country you are, has to be, for the reason of not blowing up some power plant somewhere, highly regulated. Has to be very, very precise. So this is a time base which is super precise. Yes, it drifts a bit forwards and backwards, but it actually drifts very symmetrically. So the average frequency which you get on the grid is very precisely 50 hertz. If all countries all across Europe have to synchronize on that because it's one power grid, those 50 hertz, this 50 hertz frequency is very dependable. And that is the classical bedside clock in Europe before wireless became so cheap that you built this in every clock anywhere. They were just synchronized on the grid, which was also pretty precise. Of course, you have to set them once, but then they're actually staying very precise for a long time. Besides the one funny day in West Berlin, after they opened the wall, and they reconnected the power grid with Eastern Europe. And that day, every school kid in Western Berlin was 20 minutes late because all the clocks which were synchronized on the grid went way off. Because the power grid was actually getting completely out of whack. Which I found funny as a reminder how much we depend on those kind of infrastructures in our environments here. Of course, Australians are independent of that because they don't assume that the grid is stable or that we have any frequencies in the air anyway. So we're all on our own here, setting the time anyway. Okay. So, from your programming language perspective, after we define time, the next question is resolution, accuracy, and duration. How long is your time running? Or is that a question? Do you have to ask, how long is my time running? Is that running forever? Yeah, you have limited sized counters, and you have a few counters which are running completely asynchronous for a long time, but most of your timers, which you will use in your real-time systems, will have 16-bit clocked very reasonably fast. Eventually they will roll over. So you have to also always consider, I measure my time here, but I'm better done in so and so many hours because my timer is actually running over. So you need to think about this as well. What is my accuracy, my resolution, and how long can my time actually run?
Is it that hard to just put a 64-bit counter in all the microprocessors and don't have to worry about that problem for 50,000 years or whatever?
Yes, but you also want to measure a lot of times. So you have many independent timers running everywhere, and they are not all 64-bit wide, and they're also in your control. You control the frequency of these things and how fast they're actually counting there. Maybe if you put all of them 64-bit wide, there would be a solution for that. But actually counters are large. So that takes quite some territory on your chip if you actually make them bigger. Hence, if you still look at CPUs today, you still see the size of the registers and counters. Those are actually reasonably large entities. Otherwise, it would be easy to just make them all 64-bit wide. Okay. But maybe you're right. Maybe this is actually what is going to happen eventually anyway, and we don't have to worry about this then. Okay. So any further questions about basic notion of time? Did it give you a bit more understanding this is a hard problem? There is time protocols in the real-time world which are very different from NTP, which is working over a fluffy internet connection. But there are time protocols which are based on what you suggested, namely having wires between my hard real-time connections and using them to the maximum physical possibilities. So the only thing which makes you drift away is the physical distance from your neighboring node. Other than that, you are actually hard synchronizing them. You can see this as a slightly more comfortable form of just synchronizing the crystals of your devices. Make them all go from the same clock. Okay. Any further questions about the notion of time? We still have to interface with the whole thing and actually define this from a computer science perspective. So, next question, what is embodiment? It's a weird word. What does it mean? Why do we care? Let me put up a working hypothesis. Embodied phenomena are those that by their very nature occur in real time and real space. Let's think about this a little bit more. Where can we draw some more understanding what embodiment actually means from? Are we the first people on the planet thinking about these kind of things? Philosophers. What philosophers?
I don't know.
The philosophers which think in the world of phenomenology, for example, are a good starting point. Anybody heard about phenomenology before? Nobody at all. Shame on the engineers. Because that's really bread and butter in understanding what you're actually doing in physical interaction with the real world. Now, phenomenology is not trying to understand a universal truth, a mathematical truth about the world, but phenomenology is trying to connect what we can know about the world with the actual observation of events in the world and the environment. If that sounds familiar for any engineer building a physical device, it's exactly that. You can only, as we discussed just a second ago about time, you can only work in what you actually can measure. And phenomenology is the philosophy of building the whole system around experience as opposed to assumptions. You have to be able to measure things. A good part of our scientific approach is also based on exactly that. What you do in philosophical terms is you try to connect ontology with epistemology, trying to what you can observe to the philosophy of knowledge itself. What can you possibly know about the world? Husserl is in many ways the founder of phenomenology. If you have a sunny spare afternoon someplace and your brain is idling and you need to have a significant challenge at your hands, read some of the base articles by Husserl about phenomenology. It is a tough read, can promise you that. It's not easy, but it's very rewarding in the sense of it will really bring you back to the very beginnings of what science can possibly be. What can you observe in the real world? How can you ever be sure, and now we're coming to you observing your own brain, how can you ever be sure that what you're observing is not your imagination? How do you actually put this into the real world? This is the educated version of discussions after the Matrix. It was actually painful to look at all of these forum discussions about the Matrix, where people without any clue about these kind of things were just discussing about, everything is a simulation, everything is simulated. This is the perspective which you should be aware of from a scientific point of view. Husserl was driven, as far as I understand, from the concept of mathematics is beginning to drift away into a direction which is pure abstraction, pure formalism, without any reassurance that this has actually any grounding in the real world. So he is known to have been always highly skeptical towards pure abstract reasoning, which was another strong philosophical school at this time, until it was then broken away in a sense of you cannot do math just on its own, continuing it further and further. You always have observations which are outside the current mathematical schemes, which you have to somewhat embed into that whole thing, and then you have to expand it again. You have to know how to do that. So you cannot automate math. This was one of the big discussions which was also dominant at that time, and Husserl moved in a quite different direction. So that's fun. This is probably a name which you did hear, Heidegger. He did the same thing, he just has looked at it from a different perspective. And Heidegger tried to externalize the understanding of the world in a sense of the meaning of what you're doing, the effects of what you're doing, are in the world or they don't exist. The meaning of your interaction with the world, the meaning of you building a device, doing something, is either observable in the world, there's something happening there, or it doesn't exist. So the meaning of your system is not in your head. It is observable and reflected back into the world. Interestingly, robotics designs integrated that more and more into practical systems, in the sense of when I change my environment by a robotic system, by moving in my environment by a robotic system, the notion that my environment is, so to speak, part of my database, is part of my environment, my state at the moment. And I'm not trying to abstract that if I can directly measure that. If I have a direct measurement of whether it's currently bright or dark in my environment which I have, it is not such a clever idea to represent that internally and update that internally all the time if I can simply measure that. So using your environment as part of your state is a direct technical implication of this approach. That everything what you do does have an implication on the world. Use it. This is what actually happens there. And decoupling yourself from that by having everything internalized in a beautiful abstract mathematical MATLAB simulation someplace, and ignoring that you can directly measure that at the same time, is the classical example of you're going too far into simulation, you're no longer connecting with the physical experience which you can have. I can talk a long time about that, but I don't do that now. The dichotomy of moving away from simulation at the right point of time. Merleau-Ponty, he brought this more into a social environment. And I think the current interactions which you see, the physical changes which are being done, for example, via social networks today, can be much better understood, much easier understood if you have some background in phenomenology from the perspective of Merleau-Ponty, or more widely known probably is also what Jean-Paul Sartre has done in that. The line between action and perception has always been blurred, and it is de facto also blurred in a lot of robotics designs which are doing today. It is not considered that you can measure anything without changing your environment, and you use that rather than fight it in many robotic setups these days. We also discussed this in the environment in the context of sensor designs already. That measuring something without changing your environment is not really the common way of doing things. If you think about biological systems, how do you sense something in a biological system? You yourself, your cells on your skin. Are all of these cells which you have there, are they sensors? They are sensors, yes, but they're also actuators, all of them. You also control and interact as actuators at the same time. You have barely ever a system which is purely one directional. So, more traditional environments for roboticists in terms of going completely into simulation and forgetting that there is a physical world. An example which demonstrated to me in my research quite clearly. A colleague of mine just along the corridor was quite well known for simulation design. And so we simulated most of our robotic systems first. Excuse me. Sorry. We simulated most of our robotic systems first in a very elaborate simulation environment. And I was designing a new system which I was hoping could produce nice morphologies to move around in a more clever way. And I introduced this to my colleague. And my colleague was laughing me off. And that cannot possibly move. How do you know that? And well, if I formulate this in the right differential equations to model this whole thing, if you want me to, we can just simulate that quickly. So he simulated that quickly, and he modeled that in his simulator, and then showed to me that this thing cannot move. There's no way how this thing can possibly be moving along. I was doing it, looks very convincing. And on my way back, I'm not buying it. And now, of course, I wouldn't tell you the story if that thing wouldn't have been moving. So I was actually building it then, and was, of course, proudly moving this past his office door to make him realize that it kind of moves. And he said something which really resonated with me, which was very impressive. He looked at that thing, and in all honesty, was shaking his head and said, Uwe, that's really amazing. This thing is not going to work anywhere, in any kind of simulated world, in any kind of assumptions I can possibly come up with. It doesn't work anywhere, only in the real world. And he was dead serious about this when he said that. In that moment, the real world was for him a very bizarre exception. Something that we probably can safely ignore, because he has hundreds of other environments where this cannot possibly work. So, case settled, done. Forget about this real world kind of thing. It's noisy, messy, and it doesn't really do what I want to do in a simulation environment. This is a clear indication that you have to kick your colleagues out of their simulated environments because they're actually buying into it. If you're not connecting your tests back to the physical world, that occasionally you do need to do some tests, you do need to do some measurements here. And robotic systems today are designed quite differently, and they're using the world around them and whatever you can measure for constant updating your environment. Okay. Now I would like to reformulate that with the help of Paul Deriche. Embodiment is a property of any engagement with the real world which may make this engagement meaningful. So you want to have some impact. Something has to be changing in the real world. You're not comfortable with the term meaningful, I know. But this is actually the point. Any system which you design has a purpose. Right? You're not designing this as an abstract puzzle, as an abstract game because you can. It has a purpose. This purpose is the meaning of your system. If it doesn't fulfill that, it's not working. It's not a meaningful interaction. Okay. And of course, embodied phenomena are the essence of any meaningful interaction. If there is no physical effect of what you're doing, there's no point of it. If this is only changing the state in your mind, if you're only observing your own brain, if that's all what you ever do, you're lacking exactly that embodiment which we need here. So, this has very clear implications. Two implications, one is probably more important than the other. As embodiment is the property which makes any kind of engagement, can make this engagement meaningful, that also means automatically that there cannot be something like universal intelligence. Because if you don't have any physical interaction with anything, it doesn't have any kind of meaning.
What do you mean by that? You can still have a body. So when we see everything, we need to kind of do anything about it.
Well, then you have a physical interaction there.
But that's presuming that you need to have, or do you count a purely observational, something that just observes something, is that an interaction?
How do you ever know this exists if you only observe that? If this thing can only observe, how do you know it exists in the first place?
Oh, we don't know it exists, but it could exist.
Yeah, but who cares?
Right, okay.
Yeah. And it goes the other way around. You cannot have a universal machine. Any morphology, any embedded design which you do, need to follow a specific purpose. You cannot buy the universal machine, the universal robot. Right? Now this is the conclusion of what you get if you follow any of these philosophies. That doesn't mean that you can prove the opposite. You cannot prove that a universal intelligence cannot exist or does not exist. Does that pose a problem? No. There's lots of stuff which you cannot prove, which you cannot disprove. That doesn't make it interesting. Okay. So I probably should actually start cutting it here because we are running over time already quite a bit anyway. Does that make some sense so far? Do you enjoy this slightly more philosophical excursion? Don't worry, I'm not taking this course into philosophy. We're becoming very down to earth in the next lecture again and going quite hard on bit banging interfaces as well. But you need to have a context for what you're doing here. And this is our foundation from a principal point of view. What are we actually doing here in the first place? How do we understand what the meaning of interaction on a physical device in time actually is? And it also differentiates us from the plumber. It's not only the question to get something moving in the end, you also need to understand what the point of the whole operation is. And you cannot understand it without that kind of background. Beautiful. Enjoy your weekend, guys.